This is Lab 3 Circuits, and my name is Ariana Ramatula. The purpose of this lab was to understand current and voltage differences through circuits with resistors in series and parallel, and measure the potential difference across each circuit component, and then to understand current, voltage, and capacitor behavior in a resistor-capacitor circuit in series. So the results, the calculated resistance of wire and the ammeters were 0 ohms. The calculated resistance for the 47 ohm resistor was 50 ohms. For the 100 ohm resistor, it was 105.6 ohms. And then for the capacitor, the time of discharging and charging the capacitor were equal. And the computed time constant for the 10 ohm RC circuit was 10, and for the 20 ohm RC circuit was 20. The physics principles used were Kirchhoff's loop and node rule. So the node rule says, or the current law says, that the sum of the current going into a junction is the same as the sum of the current going out of a junction. And then the loop rule, or the voltage law, says that the sum of voltage across a loop in a circuit is 0. So for the RC circuit, we know that the sum of voltage has to be 0, and therefore the voltage across the capacitor, Q over C, is equal to IR, which is the voltage across a resistor. And then we can calculate the differential equation because current is the negative derivative of charge over time, and because the voltage across a capacitor is proportional to charge, we can solve that differential equation and get delta V equals delta VO e to the negative t over RC, where RC is the time constant. In the series circuit, the current around circuit was supposed to be observed to be 0.0204 amps based on known values for the battery voltage and the resistors, but it was observed to be 18 milliamps. When the voltmeter was connected in series, the current was 1 milliamp, so much smaller, because the voltmeter has a very high resistance value. But then when the voltmeter was in parallel, the current returned to around 2 milliamps. So, or around, in the potential differences across various components of the circuit, we know that it was found to be the potential difference across the battery, A to B, was 3 volts, across the wires and the ammeter, 0 volts, across the 47 ohm resistor, or D to E, was 0.9 volt voltage difference, and then across the 100 ohm resistor, it was 1.9 volt potential difference. So when summing the total voltage difference across the loop, it was supposed to sum to 0, but it ended up summing to 0.2 volts. So likely there was a voltmeter calibration error, and this graph shows the potential differences across each circuit component. Then calculating the resistance of each of the components using the values for current and voltage we found earlier. We know that for the wire and ammeter, resistance was 0. For the 47 ohm resistor, the resistance was voltage divided by current, which is 50 ohms, and then for the 100 ohm resistor, it was 105.6 ohms. For the RC circuit, the resistor was a 10 ohm or 20 ohm light bulb. The capacitor was 1 farad capacitance, and then the power source had a voltage of 3 volts. The time to discharge and charge for the 10 ohm RC circuit was around 13 seconds, and then for the 20 ohm RC circuit, it was around a minute. So we know that the time to charge and discharge are approximately equal, but the experimental values for time quadrupled when resistance doubles, and so that does not match up with model because the time was supposed to double when resistance doubles. The time constant for the 10 ohm circuit was 10, which is resistance times capacitance, and then for the 20 ohm circuit it was 20. So this graph is the voltage on the y-axis versus time, and it is a representation of the exponential graph I mentioned earlier. And so clearly in the model, we see that the time for the voltage to go to 0 should be around 30 seconds for the 10 ohm circuit. The 10 ohm circuit was much faster than that. It was around 13 seconds. And for the 20 ohm RC circuit in green, it does match up. It's around a minute. And this is a linear representation of that same graph. The experimental value for discharge and charge for the 10 ohm circuit was supposed to be expected was supposed to be 30 seconds, and for the 20 ohm it was supposed to be 60 seconds. So if the capacitor was just attached to the battery with no resistor, ideally the capacitor would charge instantly, because resistance would be zero in the circuit, so current would be infinite. And but in reality, the wires have resistance, so resistance is not actually zero in the circuit, and therefore current is not infinite. The capacitor would charge very, very fast, but it would not be instantaneous. So sources of error, the voltmeter and ammeter are clearly likely not calibrated right. There was human error in measurement, until as maybe circuit components weren't connected properly, especially in the RC circuit. Overall, though, data and the results are as follows.